All right, everybody, welcome back from fall break, exams, etc. We are now going to enter the second part of the course, which is the part of the course dealing with sound and with hearing. And I will do what I can to make this information as accessible as possible. I know probably most of you who are in this course are interested at some point in pursuing graduate study in speech-language pathology rather than audiology. But I want to make sure everybody understands that there are a lot of good reasons to have an appreciation for sound and the way human beings shape their head and neck regions in order to produce specific sounds that will be understood by the listeners. As we all know, to speak out loud without any hope of being understood is often, I guess, often called a prerequisite for being crazy. So let's make sure we understand how sound works, how we manipulate sound to be understood, so that when you try to make the connection between speech and hearing, the connection is one that is perhaps more intuitive than it might otherwise be. I'd like to start this section of the course by defining very carefully what we will consider as the prerequisites for a sound. And so we're going to say that by definition all sounds require three things. One is a vibrating source. The second is an elastic medium. And the third is a receiver. And the receiver is defined essentially as something, either an organism or a device, whose physical state will be modified, it will be altered by the energy that was produced by the vibrating source and then propagated or transmitted through the elastic medium. So in order for a vibrating source to serve as the trigger for or as the source of a sound, we recognize that it has to be able to vibrate. And for something to vibrate, at least on the planet Earth, following the physical laws that we know of, an object has to have mass and stiffness. So mass just means that it has to have matter. It has to contain matter. And stiffness means that whatever the object is, when its shape has been changed, it needs to be able to, or it needs to have some force that's going to drive it back to its original shape. So we're going to say that mass is linked to what's known as the inertial force, and that stiffness is linked to what we would think of as a restoring force. So for vibration to occur, there has to be an interplay. There has to be a trade-off between the object's inertial force and its restoring force, and we'll see that in just a few moments here. We do need to be able to define some characteristics of vibrations, and we're going to stick with some pretty basic ones here. So the rate of vibration, that is to say the rate at which the object vibrates back and forth. You can think of a guitar string, you can think of a piano string, any number of things. That rate of back and forth vibration is the frequency. And I think we would all agree that the higher the frequency of vibration, the higher the pitch that we hear. So by definition, pitch is the psychological correlate. It's the psychological event that, for a human listener anyway, captures this physical nature of the vibration that we're going to call frequency. We're going to measure frequency in hertz, which are abbreviated Hz. Another way to think of the frequency of vibration is in terms of cycles per second. Now, this idea of a cycle, again, think of a vibrating object that moves back and forth. One complete trip through its excursion, if you will, is one cycle. and the amount of time that takes to be completed is termed the period of the vibration. So for example, if I've got a vibrating object that vibrates at 1 cycle per second, then it completes, because it completes 1 cycle per second, its period would be 1 second. If I had another object that vibrated at 1,000 cycles per second, that would be a 1,000 hertz sound or vibration, and its period would therefore be 1/1000th of a second. So clearly, the slower the rate of vibration, the longer it takes for that object to complete 1 cycle of its vibration in any given amount of time. And we'll usually use seconds as the amount of time for vibrations. The size or the power of the vibration is termed its amplitude or its intensity. And we will also see how that refers to the amount of displacement that an object experiences excuse me, from its resting position. And then the total amount of time that a vibration lasts is termed its duration. So that's the vibrating source. With respect to this elastic medium, that is essentially another way of saying that the medium, just like the vibrating source, can have its shape changed, and yet it will be under some force to go back to its original shape or its original configuration. For us, living on land and breathing air and communicating through the air as we do, our medium is the atmosphere when we talk. When killer whales talk to each other, their medium would be the water. So you can transmit sound through any variety of media, and here we have listed air, fluid, and solid. But just recognize that all of those media have this property wherein they can be compressed or stretched out and still be under some force to return to their original configuration. When we think of transmitting sound through the air, such as when we talk or sing or clap our hands, it's important to recognize that the vibratory energy that was provided by the vibrating source, that amount of energy will dissipate or decrease as the sound wave, as this wave of displacement or this wave of pressure passes through the atmosphere. And that's why, of course, sounds do not travel infinitely far. The friction caused by the expansion and compression of the medium is going to eventually damp out the sound wave. And that might be a little bit easier to see here. Recognize here we've got a vibrating source that would be located right about there. And you see that the vibrating source pushes together in some areas those air particles. Hope you can see that arrow moving across the screen. There's the arrow again. And here you see, again, a region through which the air particles are close together is what gets pushed across the screen. It's not like the particles themselves move all the way across the screen. Now let's hook up to a particle here. See how it just goes back and forth, back and forth. So each individual particle of the medium just goes back and forth, but because they alternately get pushed together or spread further apart, that condensed area or that rarefied area is what will move across the screen in this case, or across the room, or across the backyard. These areas where the particles are squeezed together are called compressions. These areas where the particles are pulled further apart from one another are called rarefactions. And so if I'm an observer standing right here on the screen, notice how alternating regions of high pressure and low pressure will wash over me. Here, I'm going to do that again. Here I am standing on the screen. High pressure, low pressure, high pressure, low pressure. And you also see how periodic those waves are as they wash over me. That is indicative of a vibrating source that is vibrating periodically, such as, oh, I don't know, maybe your vocal folds, which if you were to just vocalize a vowel, would have that same property, the same property of displacing the air. Okay, so this is a pretty nice diagram of that, and hopefully for all of you looking at this, you can see that it's actually moving. If not, somebody please let me know, and I'll try to work out another way to get this animation to you. So we have a vibrating source. We have a medium, as we just saw, that's going to transmit the energy from one place to another. And we also have to have a receiver present in the environment whose physical state will be modified by the energy associated with that vibrating source. The physical state for us that's going to get modified will be the result of a transformation, and much more on this later, but a transformation from the mechanical energy of a sound to a neural event. And so our physical state is altered by the presence of sound energy because our neurons get excited and we have nerve impulses that result from the stimulation of our auditory pathway. As we'll see when we look at the inner ear, the main function of that auditory mechanism is to transform or transduce energy of one form into another. And so for sound, it's going to be the transformation of sound energy, which is a mechanical form of energy, into nerve energy, which is bioelectric. Just to kind of wrap this point up, if we're defining a sound as requiring a vibrating source, an elastic medium, and a receiver, then we should be able to answer the question, if a tree falls in the forest and there's nobody there to hear it, did it make a sound? Well, what do you think? Obviously, if there's no receiver, then no. The way we have defined sound, there is no sound. So the next time any of you are out at a gathering of friends or enemies, you can use this as a way to kind of show off how much you have taken from school. So now you know the answer. If a tree falls in the forest and there's nobody there to hear it, does it make a sound? The answer is no, as long as we define what a sound is carefully. And don't tell me about a squirrel who's standing there and hears the tree fall, because then there is a receiver, isn't there? You know, squirrels have the same inner ear mechanisms that we do, and they perform the same kind of function on sound. So if it's just a squirrel there, then sure, there was a sound. All right, now what about this vibrating source? What about this interplay between the inertial force and the restoring force? Well, I'm going to probably jump back and forth here between this slide and the next one as a way to try to illustrate this point. So this is just a sine wave. Those of you who've had a little math will recognize it as such. And what we're looking at on this graph is the motion of some vibrating object. One way to think about this would be and if we were actually sitting in a classroom, what I would do is I would have a yardstick, and I would turn it so that I was pointing it at the class almost like it was a sword, and all you'd be able to see would be the very tip of that yardstick. And then by placing it on the tabletop or even just holding it, I would set the thing into motion up and down so that you would be able to see just this little point at the end of the yardstick moving up and down. So that's what this is. This is the actual movement of the yardstick up and down, and it's just superimposed on the passage of time. So it's not like that I hit that yardstick and it just goes up and down once and then stops. No, it actually keeps vibrating up and down, right? And what we're going to look at is how that vibration is actually maintained by the trade-off between the forces of both inertia and the so-called restoring force. So back to this slide. The restoring force is going to act on that object as soon as I displace it from its resting position. So when I hit that yardstick, perhaps in the down direction, you all would be able to follow its movement downward. And then after a moment or two, you would recognize the yardstick is no longer moving down, it's actually moving back up again, right? Moving back toward its resting position. And it does that because it has stiffness or restoring force. So if I displace that object from its resting position, it's under force, it's under some force to actually go back to its resting position. The problem is that once it starts moving here away from its resting position, the restoring force is going to pull it back up, and as soon as it starts to come back up toward its resting position, it now has energy driving it back in this direction. And it's not like the object stops at its resting position. No, it keeps going beyond that resting position because now it also has inertia. So if you want to look at it in very practical terms, think of restoring force as always driving the object back to its resting position, which is indicated here on this 0 line or point C. Think of inertia as always driving the object back in whatever direction it happens to be moving. So here, the restoring force pulled the object back to its resting position, but now because the object was already moving in that position, it has inertia, and the inertia keeps it going even further away from the resting position. Well, as you would imagine, as soon as it starts to move away from its resting position, that restoring force begins to pull it back. It takes a moment because of all the inertia that the object already has moving in that direction, but at some point the amount of restoring force is enough to overcome the amount of inertia. The object actually stops vibrating for a moment, stops moving for a moment, and then begins to head back to its resting position. Another way to picture this is to picture yourself on a swing going back and forth. Now, of course, it would probably look a little better if this graph was flipped a little bit, but imagine you're going to pull some little kid or push some little kid on a swing. You pull them all the way back to your left. Let's say you're looking at the kid and their back is sort of toward your left. You pull them all the way back, and now you release them, and they start to swing, right? Now, the restoring force associated with that vibrating system will pull the kid back to the resting position, which is where the kid would be sitting if the swing wasn't moving. Obviously, that kid goes through that area, goes through that spot because the kid has inertia. And at some point, the restoring force and the inertia will become equal in magnitude. The kid will momentarily stop on the swing in midair and then reverse direction. Now the kid is moving back toward where they started, but here they were moving kind of forward toward their front of their face in an anterior direction, if you will. Now they're moving dorsally. Now they're moving with their back first, right? Moving back to your left. And again, they don't just stop when they get to that point where the swing would sit at rest. No, they keep going because they have inertia, and they make it all the way back almost up to where they were before when you first let go of them. But if you don't push them again, they don't go quite as far. And again, they actually stop and reverse direction and start heading back. We see here mass and inertia, so we're going to recognize that the amount of mass that an object has is proportional to its amount of inertia. Elasticity is actually the inverse of stiffness. So the more stiffness an object has, the more restoring force it has. This is a little bit unclear in that regard. But it's important for you to recognize that the forces associated with mass and stiffness or mass and elasticity will be what dictates the rate of the vibration. Notice that the vibration's rate stays the same, the frequency stays the same, even as the amplitude drops down almost to nothing. In other words, the same amount of time passes per cycle throughout this graph, even though the amplitude is decreasing. And again, if you didn't push that kid on the swing, I think you would agree that as time goes on, the excursion of that kid through that resting position would get smaller and smaller until finally the vibration or the swinging would be damped out and the kid would no longer be moving. Just as another way to picture these interesting spots here and here and here and here, think of being on a swing yourself and trying to swing very, very high. There have probably been times when if you've really tried to go really high on a swing, where you've almost felt like at the top of each sort of side that you went to, didn't it almost feel like you were falling off the swing? In fact, the thing might have even slipped out from underneath you, the swing part, and you found yourself holding on to the chains really hard because you realized that your support area there had kind of slipped out from underneath you. That's what happens when you stop moving in midair and there's no more centrifugal force holding your bottom onto the swing. The swing actually seems to slip away from you. For those of you who have not yet tried to swing so high on a swing set that you actually make it over the top, I recommend caution, but I do recommend that you try doing that. It is, I think, still a lot of fun, and you'll really see how you actually do stop moving in midair at these specific locations here. What else on this? Well, we do want to recognize that there is this idea of damping, and that the more highly damped a system is, the shorter the duration of its vibration will be. The less damping there is, the longer its duration of vibration. And the idea of phase is captured in regard to the actual location of that vibrating object at any given moment along its course. Again, in fact, the thing is just vibrating back and forth like this, but we're just looking to see how over time that vibration changes or diminishes or doesn't, depending on what's happening. But the specific location along this excursion is referred to as the phase. By convention, the zero crossings, that is to say the point at which the object vibrates through its resting position, will either be 0 degrees or 180 degrees, and that means this is going to be 90. Again, that's 180, 270, 360, or 0. It starts over again, so you'd go 0, 90, etc. Out of all these measures, phase will probably be the one that we focus the least amount of attention on. Frequency, amplitude, duration, those are going to be the ones that are a bit more critical. Hang on just one second here. And period as the inverse of frequency. Okay, so we've got a vibrating source. We've got an elastic medium. We've got a receiver. And now what we want to have an appreciation for is how the atmosphere, how our ears actually filter or modify the energy associated with a sound. Now, you've probably already had some experience with filtering when you considered the action of the vocal tract, and you saw how for different articulations or for different vocal tract occlusions or dilations, different frequencies were emphasized. And it was through the manipulation of those different frequencies that a talker was able to produce sound that could be interpreted correctly or appropriately by the listener. So there are different kinds of filter functions that we want to be familiar with, and I'm going to review those now. Those would include low-pass filters, high-pass filters, band pass and band reject, and here they are summarized. And here's a schematic or a little graph called an amplitude spectrum that will perhaps help us with this description. So on an amplitude spectrum, it's always important, and this is something that I will be counting on you in terms of any formal evaluations. In other words, when I ask you to label axes on quizzes and tests, what I mean is you label the axes on an amplitude spectrum in this way, where you have amplitude on the y-axis and frequency on the x-axis. Amplitude can be recorded in terms of decibels, frequency again in terms of hertz. Recognize that this graph, like so many others you have experience with in your life, is just a depiction of some value on the y-axis as a function of some value on the x-axis. So with an amplitude spectrum, what we're going to get is an idea or a measure of how much energy there is distributed across frequency. In the simplest case, we would have a pure tone stimulus with some specific amplitude, and you would picture that in the following way: a straight line at the frequency at which the energy is contained. And so here we have a 40 decibel pure tone at 1,000 hertz. Now, we can also use this same kind of graph to depict different kinds of filter functions. So now what we've got is energy covering this region here, and that would be consistent with the idea of a low-pass noise, that is to say, low frequencies, frequencies below 1,000 hertz, are being passed by whatever system we've got here. Let's take another look at that real quickly. So again, the cutoff for our noise is going to be 1,000 hertz, and we're going to say that the average level of each component is 40 decibels. Now, this graph right here is actually kind of a shorthand, an abbreviation, indicating that there would actually be energy at every one of these frequencies averaged out to about 40 decibels. And so for shorthand, or for simplification purposes, is that a word, in order to simplify things, we just draw a line across the top here, and we understand that there is energy filling this band of frequencies. And because we have a sort of a high frequency or a top frequency of about 1,000 hertz, we recognize that all of these other frequencies are being passed. So this would be a diagram of a low-pass noise with a 1,000 hertz cutoff. You could also just eliminate that colored in area, and that would show you basically the same thing. All right, well, what if we want to depict a high frequency or a high pass filter? Here we've got our cutoff again at 1,000 hertz. We've got our so-called spectrum level at 40 decibels. And now what we're going to do is we're going to fill in this whole area, indicating that all the frequencies above 1,000 hertz are being passed. And of course we'd need to add an arrow here technically, because the energy associated with this noise, if it's truly high pass, would extend out further than that. But in any event, what you recognize is that all the frequencies above 1,000 hertz are passed in this case. And we would call this a high pass noise, or a high pass filter function with a 1,000 hertz cutoff frequency. Now, what if we have a more well-defined band of noise, one that perhaps occupies the space between 1,000 hertz and 2,000 hertz? So here we've got the two cutoff frequencies for that. We've still got our 40 decibel amplitude or spectrum level, and now the area filled in is just in this narrow region. Now we know what the lowest frequency that's passing is, and we know what the highest frequency that's passing is, and we understand from the colored in nature of this, or even if we didn't color it in, we would understand from this diagram here that there was, because this line is across the top, energy at every one of these frequencies in between 1000 and 2000. That means there's energy at 1001, 1002, 1003. That means there's energy at 1005.78126 hertz. All the possible frequencies in that region would be represented. Whoops, let me go back to that again. So again, we're seeing a band pass noise, and the pass band for that noise is 1000 hertz to 2000 hertz. The high pass cutoff is at 1000, right? Everything above 1000 is being passed. And the low pass cut is 2000, so everything below 2000 is being passed. When you add these together, all this stuff gets eliminated, gets filtered out, and all that passes is what's in between these two cutoffs. It's also possible to filter out a specific bandwidth and allow to pass low frequency energy or high frequency energy. So let's see what happens here. Now we're going to color in these two bands. We've got the arrow going out here, and we know now that the high pass cutoff for this filter is at 1000 hertz. In other words, oh, Mark, that's wrong. No, that's right, that's right. The high pass cutoff is at 1000 hertz. That means that everything lower than 1000 is passing. Sorry about that confusion, everybody, there momentarily. And the low pass cutoff is at 2000 hertz. That means this is the lowest. 2000 hertz is the lowest frequency for that band, and that is that part of the filter is passing everything higher than that. So whereas here we had just the area in between the cutoffs passing, now here we've got everything outside that region passing. Typically, the band reject, and that's what this should be called. It's not really a band pass noise. This should actually be a band reject noise. I apologize for that. Is typically just used experimentally. The band pass noise, which is what this is used for a variety of different masking type experiments, or even for developing masking devices for people who have tinnitus. Now it's possible, and I'm kind of hoping, that all of you have seen graphs like this before when you were talking about different vowels. So here we see each individual component of a sound, of a vowel, and this would be, well, I don't know, can anybody tell me what this vowel would be, where there is F1 at 500 hertz, F2 at 1500, and F3 at about 2500 hertz. It looks like the schwa vowel to me. And what we would recognize is that there are actually different levels for these different harmonic frequencies that comprise this vowel. Now here we see that the tops of those lines are connected, and that's just to give you a better picture of the profile of that vowel sound. Here we've got one that has a pretty high F1, a low F2, and a high F3. That might be like an aw type vowel, I'm guessing. But in any event, you can see how these individual lines here represent, say, these individual lines here, where there actually is energy at these frequencies. And because this is hertz, I'm going to say that's 100, 200, 300, 400, 500 hertz, 600, 700, 800, 900, 1000, etc. And you see how there are actually peaks in the spectrum of that sound. These peaks are formed by vocal tract resonances, which by now you should know as formants. And so here's just another way to picture the different kinds of filters that I showed you earlier. But recognize that each one of these little peaks there is kind of similar to one like this, right? There's generally, with speech sounds, more energy in the low frequencies than there is in the high frequencies, and our vocal tracts do have a kind of a low pass characteristic to them under many vowel conditions. But just recognize this is yet another way to draw or to think about the filtering examples that I gave just a few moments ago. Okay, so we want to recognize that with respect to filtering, we all have a lot of experience with this. The bass and treble controls on your stereo or in your car or whatever device you use to listen to music or whatever you listen to, typically there is going to be some way to shape the frequency characteristics of that sound. If you turn the bass control up or the bass knob up, that acts like a low pass filter and actually increases physically the amount of low frequency energy passing through your system. The treble control does the same thing except with high frequencies, so it increases the high pass nature of the sound. And there are other elements such as the selectivity or tuning of specific filters that we call upon when we, for example, listen to the radio in our car. It's not as evident on cable TV as it was in the old days when you had an actual tuner that you moved around. But in any event, we want the tuning device for our TV or our radio to be able to include energy from just one specific bandwidth while filtering out all the others. And in that way, you can tune into, if you will, one station at a time. So this, a lot of that information with respect to frequency and displacement and damping is summarized on this slide right here. And let me just walk you through some of these abbreviations here. F is short for frequency, and 1 over T means 1 over the period of whatever that vibration is. So again, if I've got a frequency of, say, 100 hertz, that's 100 cycles per second. That means that each individual cycle lasted for 1/100th of a second. So the period and the frequency are inverses of one another. Same thing with the wavelength. The frequency and the wavelength are inverses of one another. The wavelength is simply the amount of physical distance, the space between the compressed area of the sound wave versus the rarefied area of the sound wave. So remember that moving diagram that we had several slides ago, and I'll just kind of scoot back there real quick. Pardon me if this is making you nauseous, I'm sorry. So in terms of wavelength, the distance from here to here would be the wavelength. So pick any peak you want, and the distance across peaks there would be the actual physical wavelength in terms of distance of that sound. We mentioned before that the more highly damped an object is, the shorter its duration will be. It's also true that for equal amounts of energy put into a vibrating system, the displacement and the frequency will be inverses, which makes sense if you have to vibrate an object back and forth, or if an object vibrates back and forth very quickly, it probably doesn't move too far from its resting position, right? Because it has to go through those cycles so quickly. And then we're going to see some examples in a moment of this so-called resonance frequency, which is a crucial element of any vibrating system. And we will see how it is proportional to the ratio of the stiffness to the mass. So what does that mean? Well, here's a nice definition of resonance itself. And essentially, an object vibrates at its resonance frequency when a force is applied to it. Of course, it has to have mass and stiffness. And then a force is applied to it. And in response to that applied force, the object will vibrate back and forth. Again, think of a guitar string. That's a very nice example where you can pluck the string, that's your applied force. And even if you let go of the string, just let it go on its own, it will vibrate at a specific rate, vibrate at a specific frequency that we hope corresponds to a musical note. If we're in tune, it should. But you know that string keeps vibrating, right? And even as the vibration dies out, the pitch of the vibration, the pitch of that note does not change. So again, just because the string's vibration is getting damped out, that doesn't mean that the rate of vibration changes. In fact, if it did change, then it would be impossible to play any musical instrument in tune. Rather, as the vibration dies out, the amplitude goes down, but the frequency stays the same, just like we saw with the example here. And as I mentioned, just as we saw or would see with the example of pushing a kid on a swing and having that swing gradually come to rest. Now let's look at this equation, because this is what is going to tell us how we can expect the resonance frequency to act, if you will, given different amounts of stiffness or mass for the vibrating object. So if we make S a big number, then the resonance frequency goes up too. I hope you can see that, right? This is just a fraction. And if S is big, then resonance frequency will be big. If mass is big, then that number, the resonance frequency number, will be small. So we would expect smaller objects, or we would expect, stiffer objects to have high resonance frequencies. We would expect massive objects to have low resonance frequencies. Now, don't get fooled, or don't fool yourself into thinking that objects with a lot of stiffness have very little mass. That's not true at all. The planet Earth is probably a pretty stiff planet as things go, yet it has a great deal of mass as well. Why would I say the planet Earth has a great deal of stiffness? Well, I don't know. Have you ever tried to displace the Earth from its resting position? I don't care how hard you jump up and down, you're not going to be able to budge it pretty far. It's got quite a bit of mass and inertia, and also quite a bit of restoring force. In any event, there are two main ideas, or two main physical quantities that go into serving that equation. Recognize also that when an object vibrates at its resonance frequency, damping is minimized, and therefore its duration will be at a maximum. Here are just some other examples. Again, think also now, if you want to, of a guitar that you are putting your finger down on the fretboard and moving up along that fretboard. You see how you're actually making that string shorter and shorter, less and less massive, if you will, and the pitch of the sound coming out of that string gets higher and higher. Think also of an upright bass and how low the pitch is of the sound that comes off of those strings. Piano sounding boards also have the same idea. If you've ever been able to look under the hood of a piano, I think you'll find the strings do basically the same thing. Woodwind instruments also do the same thing. Reed instruments do the same thing. The larger the instrument, the lower the pitch of sound that comes out. Why? Because what's being set into motion there is the volume of air inside the instrument itself, inside the tube that that instrument contains. And so a flute has a lower pitch in general than a piccolo, because the piccolo holds much less air. The mass of its vibration, of its vibrating source or its vibrating component, the air inside of it, is much lower. Therefore, it vibrates much more rapidly. Think of the difference between a baritone sax and a tenor sax and an alto sax, or a soprano sax. The higher the pitch that comes out, the smaller the instrument, or actually it's the other way around. The smaller the instrument, the less air it holds, and the higher the pitch will be that comes out. Again, if we were sitting in a classroom, and maybe we'll do this if we have a review session sometime soon, look at different tuning forks and how the tuning forks of different frequencies actually, or that produce different frequencies, how different they look from one another. The ones that produce low frequencies are much larger than the ones that produce high frequencies. You can also imagine a child on a swing. The bigger the child, the harder you have to push, obviously, but also the longer they will tend to swing, but also the slower the rate. Pushing a car out of a ditch, you can apply a force to a car sitting in a ditch at a high rate, at a fast rate, or at a high frequency. But think of moving your arms back and forth really fast. Is that the best way to get a car out of a ditch? No, the best way is to slowly push back and forth, because that car is very massive, and if you are trying to move it, you're not going to move it by trying to get it going back and forth quickly. You want it to go back and forth at a great displacement and therefore very slowly. Now I've got a couple of movie animations, YouTube clips, that follow this. One is of the Tacoma Narrows Bridge collapsing under the force of wind blowing on it. And the other one is a glass being shattered by the presentation of a sound that stays on for a little while. I urge you to watch these two, especially this one. It's an old movie, but it's very cool. You just won't believe it if you've never seen it before. And it just shows you how when an object is set in motion at its resonance frequency, that object may actually vibrate so far at such a high amplitude that it breaks, that its elastic limit is shattered, if you will, and the object breaks. So resonance is potentially a very powerful element of sound transmission. You all have had experience with resonance when you look at vocal tract output, and indeed formants are really just another name for vocal tract resonances. And so the idea is that when an object is set in motion at its resonance frequency, its transmission of energy into the environment or to the receiver is at a maximum. What we'll see in the next couple lectures here is how the ear uses this idea, uses resonance to, in a sense, sharpen and improve or focus its neural representations of sounds so that as listeners we accurately hear what has been presented to the environment. And of course there is a band named Resonance. I don't know if they're still around. They look, again, just like rostral caudal, just profoundly lame, but you never know. I mean, wearing clothes like that, who knows? So thanks. Next up will be the start of our investigation of the ear, and of course we'll start with the outer ear and work our way in.